Seawater has a TDS level of around 35,000 to 40,000 ppm. This means every liter carries a huge amount of dissolved salt, minerals, and other impurities. So turning seawater into safe drinking water is not simple filtration. It is a major engineering challenge. For countries such as Saudi Arabia, Qatar, Kuwait, and many others, seawater is one of the only practical sources of drinking water. That is why desalination plants are so important in these regions. But desalination is not an easy process. These plants consume a large amount of energy and their pumps operate under extremely high pressure. Even collecting seawater from the ocean is difficult because the ocean is full of marine life. If seawater is drawn in too quickly, fish and other organisms can enter the system or become trapped against the intake screens. To prevent this, coarse screens are used to stop large objects such as plastic, wood, and fish. Fine screens then remove smaller material. The intake velocity is kept very low, so marine life gets enough time to move away from the suction zone. After passing through large intake tunnels, the seawater reaches the pump station. These pumps draw the water in and send it towards the treatment plant. At this stage, the water still contains a large amount of suspended and dissolved material. So before the final desalination stage, it must go through pre-treatment. The water enters a mixing tank where positively charged chemicals are added. These chemicals neutralize negatively charged particles such as mud, algae, bacteria, and organic matter. Once neutralized, these tiny particles start sticking together. This process is called coagulation. The water then moves into a flocculation tank, where it gets gently mixed. During this stage, the small particles join together and form large clusters called flocks. This process is similar to curdling milk, where tiny particles separate from the liquid and become easier to remove. Next, the water enters an air flotation tank. Air is mixed into the water to create tiny bubbles. The flocks attached to these bubbles rise to the surface and are then removed through a drainage system. After air flotation, the water moves into media filtration. This filter tank contains several layers. The upper layer is usually anthracite, a carbon-rich material from the coal family. Below that, there is a sand layer, and at the bottom, a gravel support layer. As water passes through these layers, the filter traps particles that escaped the air flotation stage, such as fine sand, mud particles, and biological material. But over time, these filters become filled with impurities. Once that happens, they cannot clean the water properly. To restore them, clean water is sent backwards through the filter. This process is called backwashing. Now, another important problem appears. Chlorine is often added during chemical treatment to kill algae and bacteria before they can block the filters. But the main RO membrane is made from polyamide, and chlorine can damage polyamide. So before the water reaches the membrane, the chlorine must be removed. For this, a chemical called sodium metabisulfite is injected into the pipeline. It reacts with the remaining chlorine and converts it into safer dissolved compounds. In simple words, the plant first treats the seawater, and then it must treat the treated water again to protect the membrane. This is why desalination plants are so complex. Many desalination plants also use activated carbon. This is often made from coconut shells. When coconut shell is heated without oxygen, it does not burn in the normal way. Instead, it becomes activated, and millions of tiny pores form inside it. As water flows through these pores, weak molecular forces known as van der Waals forces help trap organic chemicals, pesticides, humic substances, and remaining chlorine. Before the final desalination stage, the water may also pass through a cartridge filter. The cylindrical filter contains very fine pores, usually around 1 to 5 microns in size, which remove extremely small suspended particles. But even after all these treatment stages, one thing has not changed. The TDS is still around 35,000 ppm. The salt has not yet been removed. To remove this salt, the water is sent to a high-pressure pump. This is usually a multi-stage centrifugal pump. Inside it, one impeller increases the pressure, then the next impeller increases it further, and this process continues through several stages. By the time the water leaves the pump, its pressure can reach around 55 to 80 bar. To understand how powerful this is, imagine pushing water vertically into the air. At this pressure, the water column could rise hundreds of meters, roughly as high as a very tall skyscraper. So why do we need such extreme pressure? The answer lies in reverse osmosis. This high-pressure pump is usually driven by a three-phase induction motor. These motors are widely used in heavy industrial systems because they are rugged, reliable, and capable of running for long periods under heavy load. Now, the high-pressure seawater moves towards the RO membrane. A domestic RO purifier may use a small membrane cartridge. But in a large desalination plant, many membrane elements are installed in series inside long-pressure vessels. Water enters from the feed side. At the outlet, there are two streams. One is clean permeate water, and the other is concentrated brine. The real separation happens inside the RO membrane. To understand it, first imagine a membrane with clean water on one side and salty water on the other. Under natural conditions, water molecules move from the clean side towards the salty side to balance the concentration. This process is called osmosis. Reverse osmosis does the opposite. Here, high pressure is applied to the salty water. This pressure forces water molecules through the membrane, while most salts, heavy metals, bacteria, viruses, and other impurities are left behind. The active membrane layer is made from polyamide. It works at an extremely small separation scale, close to the molecular level. That is why ordinary pressure is not enough. The water needs strong pressure to pass through this layer. But this thin polyamide layer cannot handle such high pressure on its own. So it is supported by a polysulfone layer, and below that, a polyester backing layer. Together, these layers form a membrane sheet, often called a leaf. This leaf is folded, and a plastic mesh called a feed spacer is placed between the layers. This spacer creates a path for the high-pressure seawater to flow across the membrane surface. When clean water passes through the membrane, it enters another layer called a permeate carrier. This layer collects the clean water and guides it towards the central tube. Three sides of the membrane leaf are sealed with glue, while one side remains open. Thus, one side is connected to the central collection tube. The membrane leaves are then rolled around this tube, forming a spiral-wound membrane element. As water flows through the element, clean water collects inside the central tube, while concentrated brine continues moving forward. The first membrane element usually produces more clean water because the salt concentration is still comparatively low. But as the water moves through the later membrane elements, the remaining brine becomes more concentrated. Because of this high salt concentration, the later membranes produce less clean water and face a greater risk of scaling and fouling. That is why membrane performance must be monitored carefully, and membranes are replaced when their efficiency drops. At the outlet of the RO membrane system, two streams come out. One stream is clean permeate water. The other is concentrated brine. The TDS of this brine can rise to nearly 50,000 ppm, but this brine still has something valuable: pressure. Since it has just passed through the high-pressure system, it still carries a large amount of pressure energy. If this energy is wasted, the plant will consume much more power. To recover this energy, the brine is sent to an energy recovery device. Inside this device, there is a rotor at the center which fixes plates on both sides. Low-pressure seawater enters from one side. This water is taken from the feed line before the high-pressure pump. From the other side, high-pressure brine enters from the RO membrane system. As the high-pressure brine enters the rotor channels, it pushes against the low-pressure seawater and transfers pressure to it. The rotor keeps turning. As each channel moves between the high-pressure side and the low-pressure side, pressure is transferred from the brine to the incoming seawater. If we look carefully, there is no solid wall separating the two streams inside the rotor channel. Because of this, a very small amount of brine can mix with the incoming seawater. But this mixing is limited and controlled. In this way, low-pressure seawater can leave the energy recovery device at nearly 50 bar. A booster pump then increases this pressure slightly more, bringing it close to the pressure level required by the RO membrane system. This pressurized feed water is then sent back towards the membrane. The energy recovery device reduces the load on the main high-pressure pump and can significantly lower the plant's energy consumption, depending on the plant design. Now, the final brine stream cannot simply be released into the ocean at one point. Its salt concentration is very high, and if it is discharged in one location, it can disturb the local marine environment. To avoid this, the brine is usually discharged through a long outfall pipeline that extends far away from the plant. Multiple diffuser nozzles are installed along the pipe. These nozzles spread the brine into the seawater and help it mix quickly with the surrounding ocean water. Different plants may use different brine discharge methods, depending on local environmental rules and ocean conditions. Inside a large desalination plant, many membrane elements are connected in series and parallel to handle a huge volume of water. But even after the RO stage, the clean water is not always ready for direct drinking. The membrane removes most minerals, and the pH of the water can also drop. To make the water suitable for supply, minerals must be restored. For this, CO2 is injected into the water, and then the water passes through a limestone bed. The limestone dissolves slightly and adds minerals back into the water. This also helps bring the pH closer to the required level. After remineralization, a small amount of chlorine is added again. This is not for the membrane stage. This is for the distribution network. From the desalination plant, water may travel a long distance through pipelines before reaching cities. During this journey, bacteria can grow inside the water. Chlorine helps protect the water during storage and distribution. Large desalination plants in Middle Eastern countries can produce around 500,000 to 1 million cubic meters of water per day. That is roughly 5,800 to 11,600 liters every second. But this scale comes with a major challenge: energy consumption. That is why new ideas are being explored. One approach is to use deep ocean pressure. As we go deeper into the ocean, the natural water pressure increases. If a membrane system is placed deep underwater, this natural pressure could help push water through the membrane. In that case, the system would not need to generate all the pressure using pumps. The main challenge would be collecting the clean water and bringing it back to the surface. If you want more engineering breakdowns like this, subscribe to the channel. Thank you.